$6. That's all it took to kill the most revolutionary race car ever built. A bearing worth less than a tank of gas failed with 3 laps to go at the 1967 Indianapolis 500, and with it died the future of American motorsport. The car that should have won that day didn't have pistons, didn't have a transmission, and didn't vibrate. It screamed past the competition at 196 miles per hour while sipping fuel like an economy car. This is the story of Andy Granatelli's STP-Paxton Turbine Car, a machine so dominant, so revolutionary, and so terrifying to the racing establishment that they changed the rule book just to kill it. Picture this. It's May 30th, 1967, the Indianapolis Motor Speedway. 300,000 fans packed into the grandstands are witnessing something they've never seen before. A bright red wedge-shaped car, number 40, is absolutely destroying the field. It doesn't sound like any race car they've ever heard. Instead of the thunderous roar of pistons and exhaust, there's a high-pitched whine that builds to a banshee scream. The driver, Parnelli Jones, hasn't shifted gears once. He can't. There's no gearbox. As he rockets past the traditional roadsters and rear-engine cars, they look like they're standing still. He's leading by 52 seconds. The race is a complete massacre. And then, with victory in sight, silence. The STP-Paxton Turbine Car represents one of the most audacious attempts to rewrite the rules of racing through pure engineering brilliance. Andy Granatelli didn't just want to win the Indianapolis 500, he wanted to render every other car on the track obsolete. And for 171 laps out of 200, he did exactly that. To understand the sheer audacity of putting a jet engine in a race car, we need to travel back to the early 1960s. The Indianapolis 500 was in the middle of a revolution. The front-engine roadsters that had dominated for decades were being challenged by lightweight rear-engine cars from Europe. Lap speeds were climbing. Colin Chapman's Lotus Ford had shown up in 1963 with a tiny 256 cubic inch engine and nearly won, proving that lightweight and efficiency could beat raw power. The traditional American approach of bigger engines and more cubic inches was under threat. The United States Auto Club, which sanctioned the Indy 500, had relatively open rules. The rulebook specified maximum displacement for piston engines, 256 cubic inches for supercharged engines, 171 cubic inches for stock blocks. But there was a curious allowance for any other type of power plant with no displacement limit. It was a loophole big enough to drive a turbine-powered car through. And that's exactly what Andy Granatelli intended to do. Granatelli was already a legend in racing circles. The CEO of STP Corporation, he'd been trying to win the Indianapolis 500 since 1946. He'd entered supercharged Novi engines that produced incredible power, but kept breaking. He'd tried everything conventional racing wisdom suggested. By 1961, he was ready to try something completely different. That year, John Zink brought the first turbine car to Indianapolis, a crude attempt that was more proof of concept than race car. It qualified but crashed early. The idea was planted. Here's where it gets interesting. Granatelli didn't just want a turbine car. He wanted the perfect turbine car. He partnered with Ken Wallace, who had been developing turbine technology for automotive applications. Together, they approached Pratt & Whitney, the aerospace giant that built engines for military helicopters and aircraft. What they had in mind wasn't some experimental prototype. They wanted to adapt the ST-6 turbine engine, a proven power plant used in military helicopters, for racing. The challenge was monumental. A turbine engine operates on completely different principles than a piston engine. In a conventional engine, pistons move up and down, converting the explosion of fuel into rotational motion through a crankshaft. It's violent, inefficient, and mechanically complex. A turbine engine is elegantly simple. Air enters the intake, gets compressed by a series of rotating blades, mixes with fuel in a combustion chamber where it burns continuously, then the expanding gases spin a turbine wheel that produces power. No reciprocating parts, no valves, no camshafts. Just smooth, continuous rotation. The Pratt & Whitney ST6B70 engine they selected was a masterpiece of aerospace engineering. In helicopter applications, it produced about 550 shaft horsepower. But racing applications are different from aviation. In a helicopter, the engine runs at relatively constant speeds. In racing, you need instant throttle response, the ability to accelerate and decelerate rapidly. The engineers at Pratt & Whitney modified the engine specifically for racing, incorporating a special regenerator system that captured waste heat from the exhaust and used it to preheat incoming air, improving efficiency by nearly 30%. The final specification was staggering. The engine produced 550 horsepower at the output shaft, but here's where turbine engines get interesting. That power was delivered at 6,230 RPM at the output shaft, after reduction gearing inside the engine itself. The actual turbine wheel was spinning at 37,500 RPM. The compressor section was turning at 57,500 RPM. These speeds are incomprehensible in piston engine terms. The fastest revving Formula One engines of the era peaked at maybe 11,000 RPM. This thing was spinning 5 times faster. But horsepower was only part of the story. Torque is what actually accelerates a car, and turbine engines produce torque in a completely different way than piston engines. A typical Indy car engine of the era might produce 350 pound-feet of torque at 6,000 RPM. The turbine produced 825 pound-feet of torque. Not at some specific RPM peak, but from essentially 0 RPM all the way to maximum speed. It was like having the pulling power of a diesel truck with the top speed of a Formula One car. To harness this power, Granatelli commissioned a completely custom chassis from Ken Wallace. The car looked nothing like contemporary Indy cars. Instead of the cigar-shaped bodies that were becoming standard, the turbine car was wedge-shaped, almost triangular in profile. The driver sat on the left side, offset from center, with the massive turbine engine to his right. The engine intake was a gaping maw on the right side of the car that could swallow 4.5 pounds of air per second at full power. That's enough air to empty a typical bedroom in about 30 seconds. The chassis itself was a masterpiece of packaging. The turbine engine was mounted at a 35-degree angle to keep the center of gravity low while accommodating the large diameter compressor section. The exhaust exited through carefully designed ports at the rear, though unlike a jet aircraft, the exhaust provided no meaningful thrust. All the power went through the output shaft to a simple 2-speed automatic transaxle. No clutch, no gear shifting in the traditional sense. The driver had a selector for forward and reverse, and the transmission would automatically shift between its two ratios based on speed. The suspension was equally revolutionary. Wallace used unequal length A-arms all around with inboard mounted shock absorbers to reduce unsprung weight. The car used 15-inch wheels all around, unusual for the era when most cars ran staggered sizes. The tires were specially developed Firestones, wider than anything else on the track. The complete car weighed 1,650 pounds dry, about average for the era, but the weight distribution was unlike anything else at Indianapolis. Testing began in secret at the Chrysler Proving Grounds in Arizona. Parnelli Jones, one of the greatest drivers in American racing history, was brought in to develop the car. His first impression was shock. "The thing that got me was the sound," he later recalled. "It didn't sound like a race car. It sounded like a jet airplane spooling up for takeoff. And the power delivery was unlike anything I'd ever experienced. You'd squeeze the throttle, and there was this slight delay, maybe half a second, then this massive surge of acceleration that just kept building and building." The delay Jones mentioned was turbine lag, the time it takes for the turbine to spool up from idle to full power. In aviation, this isn't a problem. In racing, it could be fatal. The engineers worked extensively on reducing lag through modifications to the fuel control system and the variable inlet guide vanes. They got it down to about 0.7 seconds from idle to full power. Not perfect, but manageable for a skilled driver. But lag was only one challenge. The bigger issue was heat. The turbine exhaust gas temperature reached 1,650 degrees Fahrenheit. That's hot enough to melt aluminum. The engineers had to develop special heat shields and cooling ducts to protect the chassis and bodywork. They used Inconel, a superalloy developed for jet engines, for all exhaust components. The car literally glowed red-hot after a high-speed run. Fuel consumption was supposed to be the turbine's Achilles heel. Everyone expected it to guzzle fuel like a fighter jet. But the regenerator system worked better than anyone anticipated. In testing, the turbine car achieved fuel mileage comparable to the piston-engine cars, about 1.8 miles per gallon at racing speeds. Considering it was producing nearly twice the torque of its competitors, this was remarkable. The car arrived at Indianapolis in May 1967 amid massive media attention. Granatelli, ever the showman, painted it bright STP red and promoted it as the future of racing. The establishment was skeptical. A.J. Foyt, four-time Indy 500 winner, dismissed it as a publicity stunt. Roger Ward called it a circus act. They'd changed their tune after qualifying. Qualifying at Indianapolis is about one thing: raw speed. 4 laps, 10 miles total, flat out. Jones took the turbine car out and destroyed the field. His 4-lap average was 166.075 miles per hour, good for 6th on the grid. But that number doesn't tell the full story. Jones later admitted he was deliberately sandbagging, running at about 85% throttle. "Andy told me not to show everything we had," Jones revealed years later. "We could have easily qualified on the pole at over 170 miles per hour, but we didn't want to scare anyone, not yet." Race day dawned hot and humid. Perfect turbine weather, as it turned out. Turbine engines actually perform better in hot conditions than piston engines because the higher inlet temperature improves thermodynamic efficiency. As the field of 33 cars rolled away for the start, the turbine's distinctive whine cut through the thunder of the other engines. It sounded like something from another world. At the green flag, Jones was conservative. He settled into 6th place, feeling out the car in traffic. The turbine had one significant advantage nobody had anticipated. It produced almost no vibration. In a conventional Indy car, the driver is being constantly hammered by engine vibration, gear noise, and mechanical thrashing. After 500 miles, drivers would emerge physically exhausted, hands numb, vision blurred. Jones sat in relative comfort. The only vibration came from the tires on the track's surface. By lap 20, Jones started to move. The power advantage was overwhelming. Cars that could match him in the corners were helpless on the straights. He'd exit turn 4, squeeze the throttle, and that rising turbine scream would announce another victim. By lap 30, he was in the lead. By lap 50, he was pulling away. The gap grew relentlessly, 1 second per lap, then 2, then 3. The establishment started to panic. This wasn't supposed to happen. The turbine car was supposed to break, run out of fuel, or prove uncompetitive. Instead, it was making the best drivers in the world look like amateurs. At the halfway point, Jones led by 42 seconds. He was on a different lap than most of the field. The STP crew calculated he could make the entire 500 miles on just 3 fuel stops compared to 4 or 5 for the piston cars. Here's the thing about turbine engines. They're incredibly simple mechanically. The Pratt & Whitney ST6 had been developed for military helicopters, where reliability was literally life and death. It had accumulated millions of flight hours. The racing modifications were minimal, mainly to the fuel control and reduction gearbox. The core engine was bulletproof. While other cars were retiring with blown engines, broken transmissions, and mechanical failures, the turbine just kept screaming around the track. The temperature climbed into the 90s. Drivers in conventional cars were suffering in the heat, their engines running hot, oil temperatures climbing into the danger zone. Jones later described the turbine car as being like sitting in an air-conditioned office. The offset seating position meant he wasn't directly behind a hot engine. The turbine's exhaust exited well behind him. He was fresh, while his competitors were wilting. By lap 150, the race was over as a competition. Jones led by 52 seconds. He was lapping cars at will. The turbine's fuel efficiency meant he could run longer stints than anyone else. When he did pit, the stops were quick. No transmission to worry about, no clutch to burn up. Just add fuel and go. The STP crew was already celebrating. After 21 years of trying, Andy Granatelli was finally going to win the Indianapolis 500. Then came lap 197, 3 laps to go. Jones was cruising, managing his pace, when suddenly the turbine note changed. The scream became a wheeze, then silence. Jones coasted into turn 4 and rolled to a stop. The crowd of 300,000 went silent. The red turbine car sat motionless as A.J. Foyt roared past to take the lead and eventually the victory. The failure was almost insulting in its simplicity. A bearing in the reduction gearbox between the turbine and the transmission had failed. Not the space-age turbine engine, not the revolutionary regenerator, not any of the exotic materials or aerospace technology, a $6 bearing that you could buy at any industrial supply house. The bearing had been specified for 500 hours of operation. It failed after 4. Post-race inspection revealed the truth. The bearing had been running without adequate lubrication. The gearbox used a dry sump lubrication system with a small electric pump. The pump drive had failed, starving the bearing of oil. It had lasted 197 laps on residual lubrication before finally seizing. The turbine engine itself was perfect. It could have run another 500 miles without missing a beat. The racing establishment breathed a collective sigh of relief, but they knew what they had witnessed. The turbine car hadn't just been competitive, it had been dominant. Overwhelmingly, embarrassingly dominant. If not for a $6 bearing, it would have won by over a lap. The implications were terrifying for traditional car builders. If turbine cars were allowed to develop, piston engines would become obsolete overnight. Granatelli wasn't done. For 1968, he returned with not 1 but 3 turbine cars. These used a different approach. A Lotus chassis, designed by Colin Chapman with 4-wheel drive, and a smaller Pratt & Whitney ST6 engine producing 500 horsepower. The 4-wheel drive system distributed the massive torque to all 4 wheels, improving traction out of corners. Joe Leonard qualified on pole at 171.559 miles per hour. Graham Hill qualified second. Art Pollard qualified 11th. Turbines occupied 3 of the top 11 spots. Race day 1968 was déjà vu. Leonard led 31 laps before his fuel pump failed. Hill was running second when his turbine ingested debris and destroyed its compressor blades. The establishment got lucky again, but they'd seen enough. The United States Auto Club acted swiftly and decisively. For 1969, they limited turbine engines to 11.999 square inches of inlet area, roughly equivalent to a 160 cubic inch piston engine. It was a death sentence. The rule change made turbine engines uncompetitive overnight. No team would ever bring a turbine car to Indianapolis again. But wait, there's more. The establishment wasn't done. Those 1968 Lotus turbine cars had another innovation that scared them: 4-wheel drive. The system added weight and complexity, but it allowed drivers to use all that turbine torque more effectively. It provided better traction in the rain, more stability under braking, and the potential for active torque distribution. By 1969, several teams were developing 4-wheel drive systems. The governing body saw where this was heading: more complexity, more cost, more deviation from traditional racing. They banned four-wheel drive too, limiting cars to two-wheel drive only. In the span of 2 years, they'd killed two of the most significant technical innovations in Indianapolis history. The technical legacy of the turbine car program extends far beyond racing. The regenerator technology developed for the race car found applications in industrial power generation. The heat-resistant materials and cooling strategies influenced aerospace design. The telemetry systems developed to monitor turbine parameters in real-time advanced racing data acquisition by a decade. Even the four-wheel drive systems, though banned from Indianapolis, influenced development of all-wheel drive road cars. Consider what might have been. If turbine development had continued, we might have seen 200 miles per hour laps at Indianapolis by the early 1970s. Turbine engines could have been developed to run on alternative fuels. They'll burn almost anything combustible. The smooth power delivery and reduced vibration could have made racing safer for drivers. The simplified mechanical design could have reduced costs once development matured. Instead, racing remained locked into piston engine technology for another 50 years. The story gets even more interesting when you look at the human element. Parnelli Jones never got over that 1967 loss. "I think about it every May," he said decades later. 3 laps, $6 bearing. It still hurts. Andy Granatelli kept the turbine car in his personal collection until his death in 2013. He'd sometimes fire it up just to hear that distinctive scream. "We were too good," he reflected. "We scared them so badly they changed the rules. That's the ultimate compliment and the ultimate insult." The engineering details of the turbine car remain impressive even by today's standards. The thermal efficiency of the regenerator-equipped turbine was about 28%, comparable to modern road car engines. The power-to-weight ratio was extraordinary: 550 horsepower from an engine package weighing just 260 pounds. That's 2.1 horsepower per pound. A modern NASCAR engine produces about 1.2 horsepower per pound. The turbine was nearly twice as power-dense. The maintenance requirements were revolutionary, too. Pratt & Whitney claimed the ST6 could run 1,000 hours between overhauls. A typical Indy car engine of the era needed rebuilding after every race, sometimes after every practice session. The turbine had no valve adjustments, no ignition timing to set, no carburetor to tune. It either ran or it didn't. When it ran perfectly. Let's talk about what actually went wrong with that $6 bearing. The gearbox oil pump was electrically driven, powered by the car's electrical system. The electrical system got its power from an alternator driven by the turbine engine. Under certain conditions, specifically when Jones lifted off the throttle entering corners, the alternator output would drop momentarily. This shouldn't have been a problem. The battery should have maintained voltage. But the battery was undersized to save weight. After 197 laps of charge-discharge cycles, it couldn't maintain adequate voltage during those momentary drops. The oil pump slowed, oil pressure dropped, and the bearing ran dry. It was a cascade failure triggered by 10 pounds of weight savings on the battery. The rules that killed the turbine were surgically precise. The inlet area restriction of 11.999 square inches wasn't arbitrary. Engineers calculated that this would limit a turbine engine to about 250 horsepower, well below competitive levels. The rulemakers could have limited boost pressure, RPM, or fuel flow. Instead, they chose the one parameter that fundamentally crippled turbine efficiency. It was a masterclass in technical rule writing designed to kill a specific technology. The four-wheel drive ban was equally calculated. The official reason was safety, concerns about drive shaft failures, and mechanical complexity. The real reason was cost and tradition. Four-wheel drive systems would have triggered an expensive development race. Smaller teams couldn't afford it. but more importantly, it represented a fundamental departure from the rear-wheel drive paradigm that defined American racing. The establishment wasn't ready for that change. Modern racing has never recovered from these decisions. Formula One briefly experimented with turbine engines in the 1970s, but similar restrictions killed those efforts. The Chrysler Turbine Car program for road cars died partly because racing banned the technology, eliminating a crucial development platform. Today's Indy cars produce about 700 horsepower from turbocharged V6 engines, barely more than the 1967 turbine car achieved with 1960s technology. The technical specifications of that 1967 car remain remarkable. The complete engine package, including the reduction gearbox, weighed 360 pounds. It produced 550 horsepower at the output shaft and 825 pound-feet of torque. Fuel consumption at racing speeds was 55 gallons per hour, identical to the piston engine cars, despite producing far more torque. The regenerator recovered 30% of the exhaust heat energy. The compressor pressure ratio was 4.1. The turbine inlet temperature was 1,880 degrees Fahrenheit. These numbers would be impressive for a modern race engine. For 1967, they were revolutionary. Here's something that rarely gets mentioned. The turbine car was also remarkably clean-burning. The continuous combustion process in a turbine produces far fewer unburned hydrocarbons than the intermittent combustion in a piston engine. Emissions testing conducted after the race showed the turbine producing about 1/10 the carbon monoxide and unburned hydrocarbons of a comparable piston engine. In an era before emissions concerns, nobody cared. Today, that would be a selling point. The aerodynamics of the car were primitive by modern standards, but innovative for the era. The wedge shape reduced frontal area, while the flat bottom created a low-pressure zone that provided modest downforce. Wind tunnel testing wasn't common in racing yet, so the shape was developed through trial and error and educated guesses. Still, the car achieved a drag coefficient of about 0.35, remarkable for an open-wheel race car. The driver experience was unlike anything else in racing. Parnelli Jones described it as driving a spaceship. The lack of vibration meant he could actually see clearly at 200 miles per hour. In a piston car, everything vibrates so violently that vision blurs at high speed. The offset seating position gave excellent visibility for passing. The absence of gear changes meant he could focus entirely on his line through corners. The progressive power delivery, while different from a piston engine, was predictable and manageable once understood. The sound was weapon. Other drivers reported being unnerved by the turbine scream. It didn't sound like it belonged on a racetrack. Mario Andretti later said, "When that thing passed you, it was like being overtaken by a UFO. This high-pitched scream that got louder and louder, then this red blur shooting past, then the scream fading away. It was intimidating." The cost argument against turbines never held water. Yes, the initial development was expensive. Granatelli spent an estimated $2 million on the turbine program, serious money, in 1967. But the engines themselves, once developed, would have been cheaper than piston engines, fewer parts, longer service intervals, no exotic materials except in the hot section. Mass production would have brought costs down rapidly. The real cost was to the existing industry infrastructure built around piston engines. Every engine builder, every part supplier, every mechanic trained on traditional engines would become obsolete. Think about the wider implications. If turbine engines had succeeded in racing, road car development would have followed. Chrysler had already built 50 turbine cars for public evaluation. General Motors and Ford had turbine programs. Racing success would have accelerated development. We might have had turbine-electric hybrids decades before the Prius. The smooth, vibration-free operation would have redefined luxury cars. The multi-fuel capability could have reduced oil dependence. The entire trajectory of automotive development might have changed. The tragedy isn't just that the turbine car lost, it's that it was never allowed to evolve. Racing has always been about pushing boundaries, finding speed through innovation. The turbine represented a fundamental reimagining of what a race car could be. Instead of being celebrated, it was legislated out of existence. The message was clear. Innovation is welcome, but only incremental innovation within established parameters. Revolutionary change is too threatening. Today, the surviving turbine cars are museum pieces, relics of a future that never happened. The 1967 car sits in the Indianapolis Motor Speedway Museum, its red paint still bright, its turbines still capable of that distinctive scream. Visitors walk past, most not understanding what they're looking at. Those who know the story pause longer, imagining what might have been. 3 laps, $6. The entire future of motorsport hanging on a bearing the size of a golf ball. The story of Andy Granatelli's turbine car is ultimately about the tension between innovation and tradition, between progress and preservation. Racing needed the shock of the turbine car to realize how conservative it had become. The rules changes that followed didn't just ban turbines and four-wheel drive. They codified a philosophy that racing should evolve slowly, incrementally, predictably. That philosophy still dominates today. But here's the kicker. Granatelli won anyway. Not the race, but the larger battle. He proved that revolutionary thinking could dominate evolutionary development. He forced the entire racing establishment to change the rules just to stop him. That's the ultimate proof of superiority. You don't ban something unless it's better than what you have. The turbine car was banned because it was too good. That $6 bearing didn't just cost Granatelli the 1967 Indianapolis 500, it saved the piston engine industry from obsolescence. What's the rarest racing innovation you've ever witnessed? That one technological leap that made you realize everything was about to change? Drop a comment below and don't forget to subscribe if you want more stories about the machines that were too revolutionary for their own good. Because sometimes the most interesting race cars are the ones they wouldn't let race.